October 3rd, 2025. An interstellar visitor designated 3I/Atlas skimmed past Mars at mere zero point 0.2 astronomical units, a cosmic whisper in the void. Dozens of telescopes stood poised and ready, their instruments calibrated, their teams prepared. Yet the only publicly available evidence emerged from an unexpected source, a single faint signal, painstakingly extracted from Perseverance rover's nighttime photographs by two independent analysts working half a world apart. The silence is deafening. NASA remains quiet. The European Space Agency offers nothing. China and the United Arab Emirates, despite their sophisticated Mars orbiters, have released no data. The biggest cosmic encounter since Oumuamua, that mysterious cigar-shaped visitor that captivated the world, is now defined not by what we've learned, but by what nobody can verify. Did humanity glimpse the truth of an interstellar comet? Or has our closest look yet at a visitor from beyond our solar system slipped forever beyond reach? The implications for planetary science and our preparedness for future encounters have never been more profound. October 3rd, 2025. At just under 0.2 astronomical units, approximately 29 million kilometers, 3I/Atlas swept past Mars in a celestial dance that planetary scientists could only dream about. That distance, remarkably close by interplanetary standards, positioned the comet in an extraordinarily rare alignment for observation. Never before had an interstellar object approached a planet with such an extensive, coordinated array of orbiters and rovers positioned to observe its passage. The Mars Reconnaissance Orbiter, ESA's Mars Express, the UAE's Hope Probe, and China's Tianwen, one all received last-minute observation requests. Mission teams scrambled to adjust schedules, recalculate ephemerides, and prepare their instruments to capture a visitor from beyond our solar system as it skimmed past the red planet's orbit. The opportunity was breathtakingly brief. At its closest approach, 3I/Atlas moved through the Martian sky at a velocity no ordinary comet could match. The geometry was brutally unforgiving, a narrow observation window measured in mere days, and a target receding rapidly into the sun's overwhelming glare. For planetary scientists worldwide, the promise was intoxicating. High-resolution images from orbit could potentially reveal the intricate structure of the coma, perhaps even identify separate fragments if the comet was breaking apart. Spectrometers might capture unique chemical signatures that distinguish interstellar ice, formed in the frigid depths between stars, from the familiar comets native to our solar system. Every asset, from surface rovers to deep space orbiters, was tasked to push beyond its operational limits. The calculation was elegantly simple. A single well-timed image or spectrum could answer fundamental questions about the comet's origin, its chemistry, and the processes that shape bodies born around distant stars. The stakes couldn't be higher. Here was a chance to examine an untouched sample of galactic material, to test theories about planetary formation across the galaxy, and to measure first-hand the properties of an object that began its lonely journey light years away in an alien star system. As the flyby unfolded in real time, anticipation rippled through the scientific community. The world expected a flood of data and, perhaps, a clear view of the truly unknown. A faint, diffuse signal in the Martian night sky. That's all the Perseverance rover's Mastcam-Z camera recorded of 3I/Atlas during the critical hours following closest approach. The signal was so subtle it could barely be distinguished from background noise. The first to extract and publicly confirm this detection were Stephen Burns, a geologist and seasoned amateur planetary analyst, and Simon Stim3On, known throughout planetary imaging circles for his methodical, meticulous approach. Working independently on different continents, they downloaded the raw Mastcam-Z frames from NASA's public archive within hours of downlink. Their process was straightforward in concept but demanding in execution, combining dozens of long-exposure images, precisely aligning them using the Martian star field as reference points, and methodically suppressing noise until a barely there patch of light emerged at the predicted coordinates. The product is not a dramatic photograph worthy of front-page headlines. It's a carefully calibrated image stack annotated and shared online, showing the small, slightly smeared points surrounded by a faint, ghostly glow. The coma, diffuse and almost lost against the background, matches the expected position for 3I/Atlas as calculated from its pre-flyby orbit. No dramatic outburst. No sudden brightening. Just a subtle confirmation that the object crossed Perseverance's field of view exactly when and where orbital mechanics predicted it should appear. Burns and STEM 3 released their findings with appropriate scientific caution, emphasizing the signal's marginal strength and the complete absence of any visible structural features. Their annotated images, posted to X and Blue Sky, included overlays of predicted comet positions and links to their calibration scripts, openly inviting scrutiny from the broader community. In planetary science, such a detection represents far more than a mere technical exercise. It's tangible evidence that even amid embargoes and official silence, careful analysis of publicly available data can yield genuine scientific results. The faint central point in the Perseverance image stack stands as the only surface-based confirmation of 3I/Atlas's passage. Neither a breakthrough nor a disappointment, but rather a testament to what becomes possible when open data meets persistent curiosity. The auditable pathway to detecting the faint signature of 3I/Atlas begins with Perseverance's Mastcam-Z images, each a 29-second exposure captured under the Martian night sky. On October 3rd, 36 frames were logged. On October 4th, 40 more exposures were recorded. Analysts retrieved the raw data from NASA's publicly accessible archive, pairing each science image with its closest matching dark frame to subtract sensor noise on a pixel-by-pixel basis. Flat field corrections followed, using calibration files to account for variations in pixel sensitivity and inevitable dust accumulated on the optics during months of Martian operations. Frame registration presented the next significant challenge. Each image's star field was meticulously aligned against a projected Mars-centric star catalog, correcting for the rover's orientation and the slow, predictable drift of the Martian sky relative to the background stars. Subpixel adjustments ensure that even the faintest stars align perfectly across the entire stack. Outlier rejection through sigma clipping and median filtering remove cosmic ray hits and sporadic hot pixels, while masking flag any residual artifacts that might contaminate the final image. With the cleaned, aligned dataset in hand, the analysts stacked the images using both median and mean combination approaches to maximize the signal-to-noise ratio. The background sky was carefully modeled and subtracted, revealing sources hovering just above the detection threshold. The resulting stack produced a faint, slightly diffuse spot at the predicted coordinates for 3I/Atlas, matching the pre-flyby ephemeris within acceptable astrometric error margins. Photometric extraction confirmed the signal's brightness exceeded the stack's noise floor by a statistically significant margin. The detection cleared the standard signal-to-noise ratio threshold and was independently verified using open-source scripts, with all calibration steps and parameter files published for anyone to replicate. The result: a transparent, reproducible workflow explicitly designed to withstand rigorous scrutiny and minimize the ever-present risk of mistaking noise for signal. Rumors move faster than verified data. The moment faint signals from Perseverance's Mastcam-Z began circulating through planetary science communities, so did claims of brighter, sharper streaks in other rover images. The most viral example, a razor-thin line in a Perseverance Navcam frame from October 3rd, was hailed across social media as definitive proof of an interstellar visitor bright enough to see with the naked eye. Within hours, planetary science forums filled with annotated screenshots and increasingly speculative discussion threads. But the numbers didn't support the excitement. Planetary Emily, a planetary geologist known for her forensic ephemeris verification work, ran the coordinates through JPL's Horizon system. The streak's path and timing matched Phobos, Mars's inner moon, to within a fraction of a degree. Its speed, orientation, and apparent elongation all perfectly fit the predicted nightly arc of Phobos during a long Navcam exposure. The verdict spread quickly through the community. The viral streak wasn't 3I/Atlas, but rather a familiar satellite caught in motion against the background stars. A second wave of excitement centered on an October 2nd Mastcam-Z frame, showing a bright, fast-moving streak that seemed to defy straightforward explanation. Amateur analysts measured its angular velocity and compared it to predicted sky motion of 3I/Atlas. The result was unambiguous. The streak crossed a field in less than a second, at least 10 times faster than the comet's expected rate of motion. The brightness, profile, and velocity strongly suggested a near-field object or a sensor artifact, not an interstellar comet located 30 million kilometers away. Planetary Emily and other experienced analysts posted side-by-side overlays demonstrating the mismatch in both speed and projected sky path. Most community observers quickly adopted these diagnostics, refocusing attention on the genuine faint signal in the calibrated stacks. The episode reinforced an essential lesson. In planetary science, every streak demands rigorous verification, ephemeris matching velocity checks, and artifact screening before speculation gains traction. The analytical tools are publicly available, the verification process is transparent, and the community, when properly mobilized, can debunk a myth as rapidly as it spreads. Mars Orbiter stood ready with unprecedented capabilities. The Mars Reconnaissance Orbiter, equipped with its high-rise camera, could in principle deliver the sharpest images ever captured of an interstellar object from another world. Its narrow field of view and exceptional sensitivity made every exposure a calculated bet on precise targeting and split-second timing. ESA's Mars Express, equipped with multispectral imagers and the Omega spectrometer, offered different strengths: broad spectral scans for volatile gases and compositional fingerprints within the coma. The Trace Gas Orbiter, with its Nomad and Cassis instruments, was positioned to capture both high-resolution imaging and detailed spectra, searching for the chemical signatures that could definitively distinguish 3I/Atlas from any locally formed comet. The UAE's Hope probe and China's Tianwen. One expanded coverage further, each contributing wide-angle monitoring capabilities and potentially additional spectral data across different wavelength ranges. The technical promise was compelling and real. These orbiters possess a unique vantage point to observe 3I/Atlas at its closest approach, unlike any telescope on or near Earth, now effectively blinded by unfavorable solar geometry. In theory, high-rise could resolve fine structure within the coma or potentially spot fragments if the comet was actively breaking apart. Omega and Nomad, specifically designed for detecting faint gas signatures, might capture traces of unfamiliar molecules or rare isotopes, offering humanity's best chance for a genuine compositional breakthrough. Every instrument team carefully tuned their settings for maximum signal-to-noise performance, meticulously balancing exposure time, onboard data compression, and the ever-present risk of either saturating detectors or missing the target entirely. No raw images, no preliminary spectra, nothing. As of October 7th, not a single high-resolution frame or spectrum from any Mars orbiter has reached public archives. Routine quick-look images, press briefings, even raw thumbnails, all remain under embargo or delayed by processing bottlenecks stretching beyond normal timelines. The silence isn't for lack of effort or failed observations. It's a product of stringent embargo policies, substantial calibration backlogs, and, in this particular case, an overlapping government shutdown that has frozen routine data releases. The world waits, knowing full well that the most decisive data likely already exists locked behind institutional review processes and quality control procedures that prioritize accuracy over speed. Pointing a spacecraft at a moving target millions of kilometers away represents an exercise in calculated risk and precision planning. The ephemeris for 3I/Atlas, its predicted position in the Martian sky, was updated daily, sometimes hourly, as new measurements progressively refined understanding of the comet's trajectory. Each mission team relied on these constantly evolving predictions to plan their imaging sequences, but the process was far from automated or simple. Orbiters like Mars Reconnaissance Orbiter and Mars Express had to slew away from their routine science targets, often by several degrees, with absolutely no real-time feedback to confirm they were locked onto the correct patch of sky. Instrument teams programmed exposures in open-loop mode, meaning every image represented a leap of faith. Point the camera, trigger the exposure, and hope the object crossed the field during the scheduled observation window. Deep Space Network scheduling added yet another layer of operational fragility. Every data downlink from Mars is effectively a negotiation among competing priorities. Science data from multiple missions, routine telemetry, and urgent operational commands all compete for severely limited bandwidth. Even when an observation sequence executed perfectly, the raw images might sit in onboard memory for hours or even days, queued behind higher priority transmissions or delayed by ground station availability constraints. A miscommunication window, or even a few minutes drift in the ephemeris, could mean the difference between historic detection and a frustratingly blank frame. The reality is stark. No real-time tracking, no second chances, and no way to verify success until the data finally makes the long journey back to Earth. These constraints aren't failures of planning or inadequate technology. They represent the practical, immutable limits of deep space operations, where every observation balances prediction, precision pointing, and patient waiting for downlink confirmation. For 3, I/Atlas, the world waits not because of deliberate secrecy, but because the fundamental mechanics of interplanetary observation are as unforgiving as the cosmos itself. Solar geometry draws a hard, unbending line. As October advances, 3I/Atlas closes inexorably toward superior conjunction, October 21st and 22nd, placing it almost directly behind the Sun from Earth's perspective. By the second week of October, the angular separation shrinks below safe operational limits for virtually any telescope. The blackout isn't institutional policy or bureaucratic obstruction. It's simple, immutable orbital mechanics. From mid-October through early December, every ground-based observatory and most space-based telescopes are forced to stand down completely. Perihelion, the moment of closest approach to the Sun, falls on October 29th and 30th, positioned squarely in the heart of this observational blind spot. The comet's most active phase, the precious window when outbursts or fragmentation will be most likely, plays out entirely while Earth is effectively blind. Meanwhile, the continued silence from Mars orbiter teams isn't evidence of secrecy or cover-up, but rather reflects the realities of rigorous data processing. JPL's imaging and calibration teams face a gauntlet of quality checks. Every raw frame must be meticulously examined for cosmic ray hits, hot pixels, and subtle registration drift, hazards that are dramatically magnified when tracking a faint, fast-moving target. Standard image processing pipelines, finely tuned for slow-changing Martian landscapes, break down when a target crosses the sky at tens of kilometers per second. Even a minor misalignment during image stacking or a single missed artifact can create a ghost signal, a false fragment detection, or completely wipe out a genuine but faint detection. The calculation facing mission teams is clear and unforgiving. Release an uncalibrated frame prematurely and risk fueling another viral myth. Wait for meticulous review and face public accusations of delay or concealment. Internal embargoes, calibration backlogs, and the overlapping government shutdown all compound the bottleneck. For now, the world waits, not for a cover-up to be exposed, but for evidence that can genuinely withstand rigorous scientific scrutiny. Only then will the next released image actually mean what it claims to show. The working hypothesis remains standing. 3I/Atlas is a natural interstellar comet, rich in carbon dioxide, with only faint or completely absent traces of dicarbon C2, the classic molecule responsible for characteristic green chromosine in most solar system comets. Provisional reports hint at a distinctive volatile composition, and in some preliminary spectra, a possible excess of metals like nickel. However, no peer-reviewed compositional breakthrough has yet surfaced in the scientific literature. The decisive proof will ultimately come not from speculation or preliminary reports, but from instrument-verified spectra or high signal-to-noise time series data that can definitively confirm or overturn the natural comet scenario with chemical certainty. With Earth-based telescopes completely blinded until early December, attention shifts to the precious few assets still theoretically capable of observation. SOHO's LASCO C3 coronagraph will continue sweeping through the solar glare through late November. However, its limiting magnitude is relatively bright. V magnitude 8 to 9, meaning only a sudden dramatic outburst or unexpected brightening, would bring 3I/Atlas into its detection range. ESA's JUICE spacecraft, now outbound in the vicinity of Jupiter, may have a brief observational window in early November to attempt deep field imaging. Success depends critically on geometric alignment, scheduling priorities, and whether the comet's fading brightness remains within reach of its instruments. No public commitment or firm release date has been announced. The calendar ahead is clear. Watch for any SOHO C3 detections between late October and late November. Monitor ESA and JUICE mission channels for possible early November results. By late November or early December, Earth-based telescopes finally regain access, with large professional observatories and skilled amateur astronomers poised to recover the comet if its brightness permits. The bar for genuine confirmation is appropriately set high. Only direct instrument-backed evidence, resolved spectral lines, high signal-to-noise imaging, or time series photometry will definitively settle outstanding questions. The lesson is now hardwired into our understanding. Without substantially more off-Earth telescopes strategically positioned throughout the solar system, the next interstellar visitor could pass completely unseen, hidden in a geometric blind spot no single vantage point can overcome. To date, the only publicly available detection remains a faint stacked image from Perseverance's Mastcam-Z, calibrated and released by independent analysts working with open data. No high-resolution images or spectra from Mars orbiters have been published. As Earth enters an extended blackout period due to solar conjunction, official data from NASA, ESA, and other space agencies remains pending, with critical details about composition and internal structure still frustratingly out of reach. Until new images or spectra emerge, whether from SOHO, JUICE, or the resumption of Earth-based tracking in December, the strongest evidence remains a single faint signal extracted through patient, methodical analysis. And the fundamental question of what makes 3i/Atlas unique stays tantalizingly open, hovering just beyond our grasp in the darkness between worlds. November 8th, 2025, 3:47 Universal Time Coordinated. The notification pinged simultaneously across planetary science forums worldwide, not from NASA, not from ESA, from the JUICE spacecraft science team at ESTEC in the Netherlands. A single image, grainy, pushed to the absolute limits of the spacecraft's Janus camera, but unmistakable. 3i/Atlas, captured during a 180-second exposure while JUICE was conducting routine instrument calibrations near Jupiter. The comet appeared as an elongated smudge against the star field, but it was there, and it was breaking apart. Dr. Sarah Chun, JUICE's deputy imaging scientist, posted the preliminary analysis with a trembling hand. Multiple fragments detected. Nucleus fragmentation event likely occurred between October 29th to 31st during perihelion passage, estimating 4 to 6 distinct pieces based on photometric analysis. Within minutes, the image was being dissected by hundreds of analysts worldwide. The coma showed an asymmetric structure, elongated in the direction of solar radiation pressure. The brightness distribution suggested not a single nucleus, but a debris train, pieces tumbling away from each other at varying velocities. Amateur astronomer Marcus Webb in New Zealand was the first to make the crucial connection. He overlaid the JUICE image with the Perseverance Mastcam-Z detection from October 4th, accounting for the comet's trajectory and the 1-month time difference. "Look at the position angle," he posted. "The elongation direction matches perfectly. Perseverance didn't just see 3i/Atlas. It caught the comet just after it started fragmenting, possibly triggered by a close approach to Mars itself." The implications rippled through the community like a shockwave. November 9th brought the data everyone had been waiting for. NASA's Mars Reconnaissance Orbiter team, finally cleared by the ended government shutdown, released a stunning sequence of high-rise images from October 3rd and 4th. The first frame showed 3i/Atlas as a compact coma with a bright central condensation, a typical cometary appearance. But the second frame, taken just 18 hours later, revealed something extraordinary, a sudden, dramatic increase in dust production and the first hints of structural disruption in the nucleus. Dr. Naomi Call from the High-Rise team held an emergency press briefing. "What we're seeing is consistent with a tidally induced fragmentation event. When 3i/Atlas passed within $0 and 20 cents of Mars, the gravitational stress, though small, may have been sufficient to fracture an already weakened nucleus. Remember, this object has been traveling through interstellar space for potentially millions of years, subjected to cosmic ray bombardment and thermal cycling. It was structurally compromised long before it entered our solar system. The Mars Express Omega spectrometer data, released the same day, added the chemical piece of the puzzle. The spectra showed an unexpected spike in water ice and silicate dust immediately following closest approach, evidence that the breakup had exposed fresh interior material never before touched by sunlight. But it was the trace element analysis that stopped everyone cold. Dr. James Okafor, a spectroscopist at the European Southern Observatory, was reviewing the Omega data when he noticed something that didn't fit any model. The nickel-to-iron ratio in the dust was wrong. Not just unusual, but fundamentally inconsistent with any known cometary composition, solar system or otherwise. The ratio is inverted, he explained in a hastily arranged video call with colleagues. In every comet we've ever studied, iron dominates over nickel by a factor of 10 to 20. In 3I/Atlas, nickel exceeds iron by almost 3 to 1. That's not just rare, it's physically inexplicable by any standard stellar nucleosynthesis model. The data sparked intense debate. Some argued for contamination or calibration errors. Others pointed to exotic formation environments, perhaps material ejected from a neutron star merger or forged in a supernova that destroyed the comet's parent star system. Dr. Yuki Tanaka from Kyoto University proposed the most intriguing hypothesis. What if 3I/Atlas formed in a metal-rich planetary system around an ancient population 2 star? These stars formed from primordial gas enriched by the very first supernovae in the universe. Their chemical compositions would be radically different from our sun. We might be looking at material that's literally older than 99% of the stars in our galaxy. November 15th. With 3I/Atlas now fragmented and fading rapidly, the astronomical community mobilized for one final push. Every major observatory with access to the comet's position scrambled to secure observing time. The Hubble Space Telescope, granted emergency directors discretionary time, captured the fragment train in exquisite detail. 6 distinct pieces spread across 50,000 kilometers, each trailing its own thin dust tail. The largest fragment, designated 3I/Atlas A, showed periodic brightness variations suggesting it was tumbling chaotically, possibly with a rotation period of just 3.2 hours. The James Webb Space Telescope team reconfigured their schedule, turning the infrared giant toward the fading visitor. The MIRI instrument captured thermal emission from fragments, revealing surface temperatures and compositional gradients impossible to obtain any other way. Amateur astronomer networks coordinated a global photometry campaign, with dozens of observers capturing time series data to track how rapidly the fragments were fading and spreading apart. And on November 18th, the Atacama Large Millimeter Array in Chile detected something that would cement 3I/Atlas's place in history. ALMA's Band 7 receivers, pushed to their sensitivity limits, picked up a faint but unambiguous emission line at 345.796 gigahertz. Carbon monoxide, CO, pouring off the largest fragment at a rate indicating substantial subsurface ice reservoirs were being exposed to sunlight for the first time. But it was the isotopic ratio that made Dr. Elena Vasquez, the ALMA principal investigator, call an emergency science team meeting. The carbon-13 to carbon-12 ratio is 1.5 times higher than anything in our solar system, and the oxygen-18 abundance, it's off the charts. These isotopic signatures are inconsistent with formation in a solar composition nebula. We're looking at material that formed in an environment fundamentally different from our own. The data was bulletproof, triple-checked, independently verified, and consistent with the anomalous metal ratio seen in the Omega spectra. 3I/Atlas wasn't just an interstellar comet. It was a messenger from a planetary system with a chemical heritage unlike anything in our cosmic neighborhood. December 3rd, 2025, Earth-based telescopes finally regained full access as 3I/Atlas emerged from behind the sun. But the comet they found was barely recognizable. The 6 major fragments had spread into a loose cloud spanning nearly 200,000 kilometers. The brightest piece, 3I/Atlas A, had faded to magnitude 19, still detectable with large amateur telescopes, but a ghost of its former self. Dr. Stephen Burns and Simon Stim3on, the analysts who first detected the comet from Perseverance data, collaborated on one final analysis. They compiled every observation, from the faint Maz-Cam-Z detection through the JUICE discovery to the final ALMA spectroscopy, into a comprehensive timeline of 3I/Atlas's breakup. Their conclusion, published on the Planetary Science preprint server, 3I/Atlas represents the most thoroughly documented interstellar object to date, and the first whose fragmentation and chemical composition have been captured in real time. The anomalous isotopic ratios and metal abundances suggest formation in a stellar environment enriched by multiple generations of supernovae, possibly in an ancient globular cluster or the halo of a distant galaxy. This visitor has traveled not just across interstellar space, but across cosmic time, a 10 billion-year journey from an era when the universe was fundamentally different from today. By January 2026, 3I/Atlas had faded beyond the reach of even the largest telescopes. The fragments continued their journey outward, back into the void, their brief moment of visibility over. But the data remained. Over 14,000 individual observations from 89 different instruments, ranging from Perseverance's Maz-Cam-Z to the James Webb Space Telescope, the most complete dataset ever assembled for an interstellar object. Papers poured out through early 2026. Spectroscopy, dynamics, fragmentation modeling, formation scenarios. Each one adding another piece of the puzzle of where 3I/Atlas came from and what it revealed about planetary systems beyond our own. The NASA Mars orbiter teams, vindicated by their careful calibration work, released stunning time-lapse sequences showing the breakup in unprecedented detail. The UAE's HOPE probe contributed crucial ultraviolet observations that revealed hydroxyl radical production rates. China's Tianwen-1 provided wide-angle context images that helped track the fragment dispersion. In the end, the story of 3I/Atlas became a testament not to secrecy or missed opportunities, but to the power of persistence, international collaboration, and the willingness of dedicated scientists and amateurs alike to extract every photon of information from a fleeting cosmic encounter. The lesson was clear. The universe offers these gifts rarely and briefly. When the next interstellar visitor arrives, humanity will be ready with more telescopes, better coordination, and the hard-won knowledge that sometimes the most profound discoveries hide in the faintest signals. And somewhere in the darkness between stars, the fragment of 3I/Atlas tumble onward, carrying their ancient secrets back into the void. Their brief dance with humanity complete, but their story just beginning to be understood.